Good morning, everyone. This is morning section 1, July 18th, SBS. We are glad to introduce our first speaker in this morning, Dr. Chenfeng Li, to begin his talk. Welcome.
Thank you. Can you hear me? All right. Yes. Okay. So it's a pleasure and honor to be here joining this exciting and very unique conference. So I'm going to give something on modeling, data analytics, and AI in the space of engineering. To narrow it down, it's particularly about heterogeneous substances or materials in general. How many of you know about finite element? Have you ever heard about finite element? None of you? Okay, so it could be useful for me to give some background on that before I drill into the talk. I'm aware that this conference is largely about mathematics, with a small part in computer science and physics as well. So I was invited for the computer science bit. And this is because, yes, I'm from engineering, but my field of work is computational engineering. Which is rather different from traditional engineering topics, and it's fairly close to mathematics. I also have a very expensive hobby working in computer science, although I never get money from them. But I do attend the conferences like SIGGRAPH for the past 20 years. So when I ask myself, do I give a talk on computer science or do I give a talk on science in general? The secretary of the conference told me it's up to me. I then thought, given my main field is engineering anyway, and it has a natural connection with mathematics, I therefore decided to go for this a bit of technical topic instead of the computer science, where I work on animation, visual effects, etc. So I asked you the question of finite element. Finite element is these days the standard engineering analysis or engineering simulation tools. It's widely used in aerospace, automotive industry, civil engineering as well, you name pharmaceutical as well. So almost in every sector of engineering these days, when you talk about simulation using computer, physics-based simulation in particular, you will be using a finite element method, whatever tools you are using there. And this method or theory was developed largely from Swansea, the place where I work, from the early 60s. So unfortunately, I didn't have a slide about the history of finite element and Swansea. But long story short, when finite element was started in Swansea, there was no such thing about scientific computing. It simply doesn't exist. There's no such journal either. So researchers were struggling to even get your work published. The very first journal in finite element or numerical simulation in the entire history of mankind was published by Swansea people on a magazine, because the journals wouldn't accept that article. They were only recognizing experimental research or theoretical analysis. So what Swansea people did, they set up their own journals, many of them. They published their own textbooks, many of them, including the first one. They set up the first conferences and start to run many conferences. And to extend, 30 years down the road, they set up the International Association for Computational Mechanics. So these days, it's a large field with every year large conferences running worldwide. Some of the larger ones have 5,000 people attending. It has indeed transformed the world, one of the successful stories about technology development. That's 60 years of history. Some people say party is over, and I kind of agree with that. So coming to the talk for today, I'm not going to repeat finite element, although it might be a better topic here, given that the audience is less familiar with that. I'm going a bit more advanced than that. So this is about heterogeneous material modeling, where I'm going to use a combination of different methods, including modeling, including data analytics, and including AI. So what is a heterogeneous material? To an extent, all materials are heterogeneous. This is depend on at what scale you observe the material. If you, for concrete, for example, our floor is made from concrete, and you can observe the heterogeneous structure just by looking at the distribution of aggregate and cement paste that's visible. And you might be surprised, even stainless steel, which looks uniform, it is heterogeneous as well. So when you zoom in with X-ray or you zoom in with electron beams, you will discover the green structure, which is rather heterogeneous or random. Story moves on. So natural rocks are heterogeneous material as well, and toilet paper, and this can be observed by just using optical microscopes. Tennis racket is made from fiber reinforced composite materials. So when you cut the material and look at, observe the material from the cross section, you will find the carbon fibers, and then they are embedded in the resin matrix. Timber is typical heterogeneous materials as well, and it's very easy to observe the structure just under standard optical microscope. Plastic, including rubber, they are heterogeneous. Even glass, it looks transparent, uniform, but it may surprise you when you zoom in with a microscope. It's become heterogeneous as well. So, to an extent, everything is heterogeneous. When you talk about materials, especially solid materials. So what is heterogeneous material? It's a material comprising of multiple material phases, including voids. And this is an example of that. So you have the bread matrix and bread pore, and they randomly distribute across the bread body. To investigate or to understand or to predict the properties or behavior of materials, heterogeneous materials, for example, there are different ways to treat the material. The easiest way and often used in engineering context is treating the material as a uniform or homogeneous body. It could work in many cases, especially if you are talking about the structure performance of I-beams, for example, steel I-beams. And even you're talking about bridge behavior, yes, it's made from concrete, rather heterogeneous, but bridge is several kilometers long. At that scale, you may not need to consider the heterogeneity of the material. But in many other cases, it is necessary and critical to consider the heterogeneity of the materials, especially if you are using the material to its limit. In particular, for example, in aerospace industry, where you do push the boundary of your material capacity as much as you can. How do we observe the microstructure of heterogeneous materials? It used to be quite costly process, but not anymore. There are many different equipment to help you to observe the microstructure of materials. The easiest ones are microscopes, optical microscopes. Timber can be observed easily, and even natural rocks can be observed easily with standard microscopes. And then you move on with X-rays. X-ray used to be expensive equipment, but not anymore. It's very similar to the hospital X-ray CT. So that's the cost we are talking about. The only difference is that the industry X-ray that you use to scan materials is much more powerful, but it's essentially the same concept. And then you have SEM, scanning electron microscopy, which uses electron. And the cost is not that high either. These days, a desktop SEM may cost you 100,000 to 200,000 yuan. Of course, you can go up the scale to have larger ones. But in fact, it's quite widely equipped these days in university and research labs. To go down the scale, eventually you go down to the neutron scanning atomic scale, which is still quite expensive and is typically accessible, only accepted from national research labs or research facilities. Overall, acquiring the data for microstructures of various materials is no longer an issue. That's no longer a technical hurdle. These pictures image here, it simply shows an example of so-called polycrystalline microstructures. And these are alloys, basically. So all micromaterials looks like this, including steel. To investigate the behavior or even try to predict the performance of materials, let's treat all materials as heterogeneous materials for the time being. There are different ways to do so, of course, and many other scientific and engineering topics. Material scientists typically use experimental approach, which is to extent like cooking in the kitchen. You mix materials in different processes and test after it's cooked. The modern way of treating that from the computational perspective requires typically 3 steps. So the first step is material characterization. So you characterize the material morphology, the composition using primarily the microscopic imaging techniques, which we summarized in the previous slides. From there, once you know the composition and know the microstructure morphology of your material, you can then try to digitally reconstruct the structure. It's like you construct a 3D model for a building. But imagine you are doing that for something much, much smaller in the scale of microns or nanometers. And then the last step is to do physics-based simulation. So once you know the morphology, the geometry, and the composition of your microstructure, you can then simulate on the computer the behavior of that particular grain or particular microstructure, or we call that RVE, representative volume element. From there, you can then predict the macroscopic properties and even the long-term performance of your material. So there are 3 steps. I'm going to have a bit of each in this talk. We start with perhaps the easiest one. We call that characterization of heterogeneous materials. So this simple diagrams shows what heterogeneous materials looks like, or all materials what it looks like when you zoom in to the proper length scale. So you basically have multiple faces. In this case, we have 3 faces, gray, white, and black, randomly distributed across your material medium. To capture this geometry or this morphology, there's a simple way. You simply introduce a flag variable, like this I here. So I would be, because you have a finite number of faces, so you could use the integer to capture them. So I equals 0 if it's black, I equals 1 if it's a gray face, and I equals 2 if it's the white face. I is of course a function of space. Because of the randomness of this distribution, I is of course a random variable as well. So then it is a variable dependent on the location and it's random. Therefore, it's a random field. In 2D, it's a 2D random field. If you're talking about 3D material, it's a 3D random field. So how do we capture or quantify this random field? In general, when you talk about the random field or random process, you would say you need a joint probability distribution function, right? Or joint probability distribution in general. It won't work in this case, unfortunately, because imagine you're talking about, in this case, this is a 100 by 100 pixel image. So you would have 10,000 random variables here. To capture that random field just in 2D, you run out of your mathematical representation capacity, unless you start to introduce assumptions. Let's say if you say the whole field is Gaussian, then you only need two parameters. But that's a very rough, very brute assumption. No material is Gaussian for a fact. So, so in practice, what engineers and researchers have been doing for 50 years, perhaps longer, is instead of dragging too much about the random field, they introduce so-called statistical descriptors to capture quantified manner the features of microstructure and its morphology. So what is statistical descriptors? The easiest one would be like volume fraction. So you might say, I have three faces, black, white, and gray. Each of them counts 30% of my material. That is volume fraction, right? That's a useful thing to know. You might even say, okay, 2-point correlation. So finding 2 points of material within the same phase or within different phase, the correlation between them. So you can do many things like this. Depending on the scientific field, people have defined different types of statistical descriptors. Visibly from, I'd say, oil and gas sector, because they deal a lot with natural rocks and they have money. So they might have defined about 40 to 50 statistical descriptors to support the study of porous materials, natural rocks in particular. And then another large sector where people research a lot about the hydrogen material structure is metallurgy, alloys in particular. When you zoom in, you see the green structure, and they are random as well. It's more complicated than that. In fact, it's not just random, it's high dimensional as well. And they have defined a lot of descriptors, maybe another 50 to 60. And then you have a field like composite materials, chemical engineering, even tissue engineering in medicine. They have defined their own descriptors. Some of these overlap a bit, some of these are totally different from each other. Overall, we might say we have 150 to 200 statistical descriptors. Of course, none of these works individually. You have to put them together, take a combination of them, and still they wouldn't even give you a comprehensive quantification of your random field. The only way to capture random field comprehensively is to go for the joint probability distribution. Or you start to introduce assumptions. Let's say if it's a one-dimensional thing, you say it's a Markov process, which again very rough and never work with real material. So to move on, I'm going to give you just a few examples of statistical descriptors. These are easy to understand. So this is the volume fraction. It's a ratio between one phase against over the entire volume of your material. Move on from there, we could have the so-called specific surface area. It's basically the surface area per unit volume. So it's another ratio where you have a surface area per unit volume. It kind of tell you how round or how irregular your inclusions are. Okay. Similarly, you can do something more mathematical, so-called Minkowski functionals. The M1 and M2, they are identical to volume fraction and to specific surface area, but you have your M2, M3 here as well. So M2 and 3 is basically an average curvature. Some of you might be familiar with this. This is the pure geometry, so you integrate the curvature and over the volume. What is this? This is a green set distribution. This is also easy to understand. So you have inclusions of different sizes. If somehow you define the size of inclusion, assume you can define that, it is of course a random variable. So the distribution of that size itself can be used as a statistical descriptor. But then the question is how you define the size of your inclusion. Say this is the pore size distribution, which is rather similar to the green set distribution. So how would you define the pore size? Say a pore looks like this. You can of course measure the longest path in the pore. That's one way to say about the pore size. You can try to fill in the pore with spheres or disks and take the largest diameter or radius of your sphere. And you could also do something like this, calculate the effective diameter by using the surface area and treating that as an effective sphere. So there are different ways of defining the size of your pore, or the size of your grains. Therefore, the result changes as well. 2-point correlation function. You can do your 3-point correlation function as well. And you can do your cluster correlation, etc. And people even use n-point correlation function by picking more points in your domain. Of course, the more points you pick, the more data you will need to calculate that indicator. N-point correlation I mentioned here. Linear path function is another interesting one. So this is to find a linear path that falls in the same phase with a probability. So that tells you how well connected your materials is. And this is because for some materials, say porous material in particular, the connectivity between phases matters. Say if you want understand how water passes through your sponge, simply know the volume fraction of your pore space doesn't help. You need to know how well they are connected. And that's where the linear path function comes to play a role. Okay, so we have many of these descriptors. Some of these, the one I have shown you here, most of them have mathematical equation. But in reality, you only have about 30 descriptors with mathematical equations, and the other 100 plus descriptors have no equations at all. What they are, how they are defined is basically an algorithm. You simply process the image, could be 2D, could be 3D, with an algorithm step by step, and that algorithm gives you a vector, and that vector is your descriptor. So the fact is that all descriptors are defined in different ways. A small percentage of them have equations. And they are not, in most cases, independent from each other. So each of them captures certain aspect of the statistical information for your material. Could be geometry, could be morphology, but surely they are not independent from each other. And then the question is, which one to use? We have 150 to 200 of them, which one to use? And why you use certain subset of these descriptors. Until recently, there was no answer to that question, apart from a few rare cases where you can mathematically derive the relationship between a few descriptors. But other than that, it's unknown, unanswered question. And this question is important because we want to use these descriptors to characterize the materials. And there are different ways to combine them. Surely you shouldn't use all of them, not only because there are too many of them, also because some of them overlap with each other strongly. If you use those overlapping descriptors, you start to introduce information conflicts. So we did a piece of work to quantify or quantitatively understand the correlation between descriptors. This is achieved, I can tell you the answer now, by using to extent machine learning or AI methods. And this was only done a few years ago. So you might say after 50 plus years of development in different fields, by proposing all these descriptors, only until recent years, this question was solved. So what is the question? The question is that we have so many descriptors. Some of them are just one number, like volume fraction. Some of them is a vector as a function. So we want to understand the relationship between all these descriptors. This is a typical, say, if we treat this question from a data analysis perspective. The challenge here is the data is not of uniform format. They are of different formats, different lengths. So it's heterogeneous data. How to understand the relationship between heterogeneous data, that's the challenge. When we realize this is the major challenge, we start to think, can we regularize the data set, meaning convert them to the same format? And then if we can do so, which we managed to do so, we end up with a much larger data format, because this uniform data format has to accommodate all these 150, 200 plus descriptors, which is not possible to analyze. So we have to do dimension reduction to make that manageable. And finally, we can do feature analysis on the reduced dimension data set. So how we did it? It took some time to figure out the solution, but once it's done, it's quite simple. So this is what we have. This is what we have. We have these descriptors represented denoted by D, and they are of different lines, different format, and we can't handle them. So what we did here is these descriptors is defined to quantify images like this. Could be 2D, could be 3D. So we pick a set of images, let's say 1, just as an example. If we apply these descriptors one by one to that image, we extract information in terms of each descriptor in different formats. We can't analyze them. But then if we use each individual descriptor as a guide to reconstruct a synthetic image, only using that particular descriptor as the target or objective function, then we might say the reconstructed images, the whole set, for each set of them, because we only use the one particular descriptor as the target to do the reconstruction. Therefore, the resulting image only captured the information or partial information from the original image. And that partial information is directly determined by that descriptor. So the logic here is if we reconstruct synthetic image from the reference and only take one guide, and that one guide to the target is to use that descriptor individually to try to minimize the difference between the reconstructed image and the original one under the measure of that one single descriptor. We end up with a set of results, and that set of results only contain a partial information for the original image, and that partial information is captured by that chosen descriptor. So what we then did is we applied the same reconstruction algorithm, the same optimization technique to build many sets of synthetic images. Each set of them corresponds to one descriptor. So then we say the resulting data sets, each set of this image capture the statistical information for one descriptor, which is of course linked to the original reference image. So again, it's biased because of that original reference image. To overcome that bias, you can pick multiple random images from different type of materials to make it more generic. But the logic is similar. So how did we do the reconstruction to ensure we capture only the chosen descriptor and nothing else? So the process is simple. We start with a random guess. It could be Gaussian distribution, and then we have our target. Each time we try to swap the pixels, and after each swap, we check if this swap makes us closer to that target, measured by a loss function, which is defined by that chosen descriptor. And we continue that iterative process until it converges. So by doing this, the loss function keeps getting smaller and smaller until it reaches the threshold. At that point, we end up with a final realization, which it contains just information, no more, no less, measured by that particular loss function, which is that particular descriptor. So we could check the accuracy of this process So after we obtained the synthetic images, we can compare the difference between them, and indeed they represent the same descriptor quite accurately. So now we basically have all descriptors captured in the form of an image, and they are for the same size, same dimension, same resolution. So it's a uniform format now. Then the question becomes, okay, forget about descriptors. We now got a bunch of images. Each set of them correspond to one particular descriptor. So the question is, it's then become a quite common computer vision problem. So you then need to classify or cluster these images to find the correlation between them. There are, of course, many different methods of doing this. When we did this, we are less knowledgeable compared to what we are now about computer vision. So we use a very basic method, which I skip some of the details here now. We basically use the k-mean clustering method. But to do that, we would have to first do dimension reduction to map the images into a much smaller vector. And we did that by using a texture spectrum. So the result is something like this. We map each image to a vector that is of 512 dimensions. They are the feature of that particular image. And then we cluster these points in this hyperspace with 512 dimensions. So this is the k-means clustering process, just as an example. The final outcome is quite simple. So the final outcome is, in this work, we studied 41 descriptors. So if you group these 41 descriptors into 41 groups, you end up with one descriptor in each group. That's easy. If you group these 41 descriptors into two groups, what you want to do is the grouping should be done in such a way that the descriptors in the same group are more similar to each other, and descriptors in different groups, they are more different from each other. So you group them based on the similarity. And similarity in this case was done or solved through k-means clustering by measuring the distance between the feature points in the hyperspace. So we have done this from 2 groups to up to 15 groups. So we might well say, it's back. So we might well say in the 2-group clustering, all the A group class descriptors are similar to each other, and all B group class descriptors are similar to each other. Between A and B, they are visibly different. We can examine the accuracy of our grouping based on known conclusions, and they all agree with each other very well. So we know a few relationships between the descriptors because they have easy mathematical representation, and we found all these existing relationships are recovered from that grouping. Okay, so that's the easiest bit of the talk. I'm afraid I will have to skip or accelerate a bit, and this is done on purpose because even if I spend more time in the next 2 sections, you will get lost anyway. Not by means of equations, but by means of the complex physics involved. So the next step is we can characterize microstructures, how we could build the microstructure to support physics-based simulation or physics-based modeling. And this is a question that has been researched for decades, many decades, I should say. What people have done is taking images directly from the microscopes and use that as your microstructure. At least for 2D, it's doable. If you have an X-ray CT, you can even build the 3D structure just from the scanning images. The limitation is, of course, availability of samples, the size, and the capacity of your equipment. So that's not ideal. Because of the randomness of these structures, you always need ideally 3D structures, and you need large structures to be able to gain a statistical representative evaluation. So an alternative way of doing that is you do a digital reconstruction. So you take the scan as your reference and you build either from 2D to 3D and also make it larger. This digital reconstruction has been researched for many decades. What people have done for until probably 5 years ago, there are many different methods. We once tried from one of my earlier PhD students to classify those methods. We end up with 14 groups, but we didn't publish because it doesn't make any sense. You'll see in a minute why it doesn't make any sense. So what people have done is, say, if we are talking about alloy materials, we know alloy is formed by solidification and then the green calcining. So when you, so alloy, take steel as an example. You burn them, the raw meal, rocks basically, in powder format with oxygen and catalyst. You burn them to 1400 degrees C, and then they melt. It's not metal yet, and then they cool. During the cooling process, solidification occurs, process kicks in, it starts to form some structures, and then you have, it starts to form grains calcining, that's a process. Eventually, the last process is phase transformation. So there are several visible physical processes occurring in that whole procedure. You could mimic artificially these processes to build your microstructure. So this was what people try to do, say using the so-called cellular automata, a strange name, but it was once popular and still popular these days to some material scientists. It sounds physical, but it's really non-physical. It's a purely artificial algorithm. You could also do that through the shape assembling. So you might say, okay, I got a bunch of spheres or ellipse of different sizes, different orientations. I just throw them into the box and then pack them to form a random structure. And by doing that, you might want to control your process such that your grain size distribution matches your descriptors, and your correlation function matches your descriptors, and maybe linear path function matches your descriptors, etc. So you can introduce explicit control or even optimization during this reconstruction process to guide your digital structure towards your reference. Monte Carlo simulation is another one. Phase field method is another one. It is a simulation method, but the starting point of the input is artificial. Therefore, the result is artificial as well. And again, you try to introduce constraint in that simulation process to mimic the descriptors extracted from the reference. Random field transformation is a pure mathematical treatment. So in this case, you could say, okay, this is my material, black and white, just two faces. It's definitely non-Gaussian for sure, we know that. But Gaussian field is easy to handle and easy to generate. The question is that possible to transform a Gaussian field? It could be 2D, it could be 3D, into something like that. Imagine you have a Gaussian field, up and pure and valley everything. If you simply cut that Gaussian field, say everything above that threshold is a white face, everything below that threshold is black face, and then you could end up with something like this. The question is, well, the feature matches that. So what we can do is, we know to capture Gaussian field, we only need two parameters, the mean and the correlation. So if we use the mean and the correlation as your target, and your only target, you could optimize your transformation It could be a plain cut, or could be something more clever, maybe a sinusoidal cut, such that it would give you the same correlation and mean of your reference. And that can be done. We did that 10 years ago. We are not the only group who did that. Our contribution there, this is 10 years ago, was until we did it, it has to be a nonlinear optimization process. But we did it in an analytical way. So we derived a semi-analytical solution to allow you to do that cut without much computation. I'll skip this. So these are the traditional methods. There are many more of them. But the common feature of these traditional methods are the process starts with the explicit characterization of your descriptors to obtain your descriptors, and then in your construction process, you introduce as much as possible, often explicitly, the constraints to bring your synthetic model, your reconstructed model, towards your target. And sometimes you do that as an optimization process, therefore you do that implicitly, like the stochastic optimization method we used in the descriptor correlation analysis work. You would all have heard these days large language models, right? The AI models and the so-called generative AI. And they have been so powerful in processing images, even videos. At this conference, we saw multiple times of those videos. They saw a woman walking on the street, all generated by the computer. So clearly, computer can these days, not computer, the algorithm, these days can generate images based on or guided by your data, right? So indeed, as early as 2017, that's long before NVIDIA cards become so powerful these days, researchers in engineering tried to use a generative AI model to generate microstructure. And that was, I'd say, looking back, a step change. So the capacity of digital reconstruction suddenly become really usable. And it's quite versatile. So it might still be early days to conclude, but personally, I believe you can almost now treat all previous methods as traditional methods, and the AI model-based or computer vision-based method as the new method. We'll see if the academic community agrees with me on that in a few years' time. We also did a few trials here, which I'm going to show you here. Any of you familiar with neural networks? Well, just superficially? Not much, okay. So forget about the equations. Focus on the concept. That might be the best to get something useful to take away. So the standard neural network, in this case, is the bottom one. And this is the so-called VAE, variational autoencoder method. You basically have two neural networks. One starts with the image, and the neural network, CNN, transform the original data into a so-called into a vector, a meaningless vector, and they call that latent space. So it's essentially a feature space, but not understandable by human. And then you take that feature vector back to the image of physical space to give you another image, and that's your synthetic image or your reconstructed model. So it has this encoder and decoder signaling. And during this process, there's no feature whatsoever in the sense of the statistical descriptors representation. It gave useful results. That was done, as I said, in 2017, and ever since by several other groups. But the problem is that until you examine the result, you simply do not know how well or how bad your reconstruction quality is. sometimes good, sometimes bad, I'd say. And the papers only show you the good one. So what we did is we embedded descriptors in this reconstruction process as part of the loss function. So in this standard VAE, you always have a loss function at the end, which get backward propagated into your neural network. So we could easily build within that loss function the statistical descriptors. And even better, because we know the relationship between these descriptors. So let's say if we need to choose 4 descriptors or 5 descriptors, depending on the computational cost we need to bear. We need to then choose from the classification we did earlier, one from each group, not to have multiple ones selected from the same group, because that will bring information conflicts. So this is an example from that reconstruction. So that's one way of doing reconstruction by bringing descriptors into the loop, the standard VAE loop. This is another way to do that, a better way. So again, so this is the standard VAE, same as we showed before. You start with the image, you take one encoder to convert the features into so-called latent space. This is simply a vector, much shorter than the original image, and it's essentially the feature space, only understandable to computers, not explainable. And then you take it back to the image, where you have a loss function. Each time you try to minimize the loss function to make this closer to that one. So what we could do is, instead of using that latent space, the meaningless vector as the feature or latent space, we could use our descriptors as the latent space. So these descriptors, they have physical meaning, and that is well understood by engineers. By doing that, we basically take the feature space, the real feature space, to the image and do the iteration. So in this process, we can explicitly monitor the convergence process in the sense of your feature, how close you are getting to your target. And the consequence is your result, it either doesn't converge, then you know you failed it, or when it converges, you know you have a good result. It's a good one, for sure. There's no need to do an examination about that. So, and of course, the cost is smaller because you don't need to train that neural network anymore. You only train the decoder. So the cost is reduced by half. And these are some examples that show the difference in terms of accuracy compared to the standard generative AI model. A better one, and the best one so far, remains unpublished, is you could use, so VAE is one neural network framework. Another one that is very popular is generative adversary network, GAN network. So the standard GAN network, you basically have 2 boxes, this generator and this discriminator. Again, they fight against each other until they achieve a good result. But again, during that process, you have no way to monitor or to understand the quality of your output. What we did here is we introduced descriptors as part of the discriminator. So there are 2 parallel discriminators. One is from the traditional discriminator, which is only considering the image as the input, fake images, and the other one we consider descriptors. And these combined together, they compete with the generator. So it's like the traditional GAN model, you have 2 neural networks fight against each other. Now we have 3, 2 on one side, 1 on the start side. And this the result is very encouraging. It is, I'd say, at least 1 order's magnitude faster than the standard GAN model without the guidance of descriptors, and the accuracy is far better. The worst thing about the GAN model is let's say you use 50 layers of neural network. It may be worse than your 40 layers of neural network. By increasing the layers or increasing iterations, it's not guaranteed your result gets better. But with our model, it converges. So as the iteration goes, the result is definitely getting better. As the layers increase, the result is definitely getting better because we have the descriptor there to explicitly control the iterative process. And these are the accuracy checks, everything. The last part is the most complicated part, and I'm going to leave the least amount of time to that part, partially because whatever I do here, you'll get lost. But I hope the concepts get passed through. So how we use the microstructure to understand material properties through physics-based simulation. I have two examples here. The first one is slightly easier. Say we have a piece of porous materials, let's say rock, sandstone, or concrete, and we want to know how water or how oil and gas pass through this piece of medium. There are many parameters, physical parameters that are relevant to this process. The single most important one is the so-called permeability. It simply quantifies how fast flow goes through a piece of solid material driven by pressure difference. Permeability is the single most important factor for the entire oil and gas sector, which has a lot of money. So they have spent a lot of resources over many decades to research rocks, largely to understand its permeability. This is the standard equipment for testing permeability. So you simply put your rock sample, a little disc, into that cell. It's a stainless steel cell, and then you have fluid coming in from one end, and the pressure, it gets squeezed to the other end. When the whole process reaches a steady state status, you then measure the flow rate balanced here. So you have the pressure difference and you have the flow rate, and then you do your calculation to find your permeability. So the physical process is add pressure between the two ends of your material and observe how flow progress through the medium, your material medium. You can of course do that process digitally, and that's so-called digital rock physics. So what you do here is you take your CT scan, not a CT scan, and build your microstructure model. On your microstructure model, for the mineral phases, you can simply treat them as impermeable. So no flow can go through the mineral phases. Flow can only go through the pore space. And then you run your fluid simulation on that model to understand how flow coming out from one end to the other end under the given boundary condition. So it's like repeating the same experiment which was done traditionally using the equipment. You do this on computer. And these are the examples. What you can do, you could do fluid simulation to understand the permeability. You can do a molecular diffusion to understand the chemical process. And you can also do heat conduction to understand the thermal behavior of your material. You can also, of course, do sound propagation as well. So you can do many things. The next step is the traditional digital rock physics requires you take the scan, put that into a microstructure model, digital reconstruction, and then you do your simulation. Simulation is faster than experiment, which typically takes months, 1 month up to 6 months to complete just on one sample. But you still need to do your simulation. And that simulation may take a day, may take two weeks. It's faster, but it requires time and requires experienced researcher to do that. Is that possible to use the AI model here so that you don't do the simulation? You simply take the scan up to here, and then you get your result. Would that be possible? It is possible. What that would require is you then need to have your data set to train your model, right? Your data set would be, you should have many of these digital reconstructions, and for each of them, you run your simulation to gain permeability, so you have that pair labeled data set. Labeled means for each of these, you have the permeability predicted from your physics-based simulation. That, of course, require a lot of pre-computation, but manageable. We tried that. So these are the rocks we considered Fontainebleau sandstone, very popular in oil and gas sector, in particular in Middle East. They are of different permeability porosity levels. And then we did, and we know we want to predict from the descriptors. So instead of predicting from the images, which is difficult to handle, imagine if we try to predict directly from the images for the probability, then the design space would be huge. Even for 100 by 100 by 100 pixel, very low resolution, you still have a million design variables. So that means you need a lot of data, label data to do the training, which is not possible. But if we use descriptors, then let's say if we only use 5 descriptors compared to 1 million design variables, your design space or your training data set requirement will become much lower. But the question is which descriptors to choose. These are examples of these descriptors. Some are single point, some are function. So we run a lot of simulations on those rock samples. Some are the original scanned sample, some are reconstructed sample. We then used machine learning process to understand which descriptors is the best one to choose. We use the so-called wrapper process, meaning we initially start with all descriptors, but then we pick the most effective descriptor one by one until we reach a subset that it is optimal. By increasing the number of descriptors, the result no longer increase or improve. I'll stop here and move to a conclusion. The next example is a bit more complex in physics. It's about alloy and crystal plasticity, everything. So for conclusion, I'd say it is now possible for the first time to reach the so-called processing, structure, properties, and performance relationships for materials. The entire material science for the last century has been more or less researching that PSPP relations. So people had always want to understand how the processing of material, how the microstructure of material affect its properties, affect its long-term performance. It's like you start cooking with meat, pork, and vegetable to begin with, and you have your cooking process. But before you finish your process, can you predict how it tastes like? It's more like that. It's never been possible, or it's been researched for over 100 years. It is now possible with the computational engineering tools we're now able to do, which include the microstructure characterization, which we now know the difference between descriptors, include the digital reconstruction, which we now have the capacity to really build large set of high-fidelity models, and the property prediction using physics-based simulation. So the last bulletin point is more like a question. We know in the history of science and engineering, people often say theory, experiment are 2 pillars. In modern days, people say theory, experiment, and computation are the 3 pillars to support innovation and research in science and engineering in general. So what's the next step? It could be called computational intelligence, given the rapid explosion or growth of AI. And that really requires integration of modeling, data analytics, and AI in science and engineering in a more organic manner, require cross-fertilization between them. It will also require perhaps fundamental developments in math. This is because The scientific reasoning in general uses the language of mathematics. Mathematics has always been primarily designed to be used by a human. All tools in mathematics have been designed in that way to be used by a human. Unfortunately, human never had a good capacity of processing data until recently. So now we do have a capacity to process large amount of data. Then the question is that possible to achieve or do data-driven scientific reasoning? The traditional scientific reasoning uses mathematics, and those tools have been designed for human to use. But we now do have capacity for large data set processing. So the question is, can we do scientific reasoning through the data or based on the data without converting that into something manageable by the existing mathematics tools? So that may require some thinking in the math to give us the proper framework or paradigm of doing such reasoning. So I will close here. Thank you very much.
Thank you very much. Very intriguing research field. Any questions?
Would you mind to turn to the 44 page in the PowerPoint?
Here?
Yes. Could you explain this process in detail about how do you compute this this Q encoder and the P decoder?
I see. Okay. Yeah. So this diagram here, this one on top, this one is a standard VAE model. VAE is a framework of a neural network, variational autoencoder. And this neural network, it has two neural networks. This is the first one, the encoder, and then the second one, decoder. The first one, encoder, is simply transform the image into a vector, and they call that vector latent space. So you could see that in mathematical science as a mapping. So you have the original image, that data set, you map that through multi-layers of a convolutional neural network, CNN, into a vector. We call that mu, sigma, epsilon, but these are arbitrary. So this is a vector. And then you use the decoder, that's another neural network, typically of the same structure as the encoder, to map it back to the physical space. And then when you map it back, of course, there are many ways to map it back. You have a loss function here to optimize the parameters in your decoder such that this matches the features of that one. So you could imagine this is the optimization process. You have the encoder to put everything into a smaller dimension, this latent space, and then you take it back to the physical space, the higher dimension, but you optimize those parameters such that the images from both ends are similar. So this is how it works in the traditional VAE. What we did here is instead of using the standard latent space, which is purely defined by the so-called encoder, we didn't use that. We use we call that simulation. It's essentially the descriptors. So we simply convert the image into descriptors and use the descriptors as the feature space or latent space. So we don't really have a neural network here as the encoder. We have the descriptors. And therefore, we only have a decoder here in this structure to map it back to the physical space. And we still do the loop with the loss function to compare with that original image and everything. So it's kind of considered the original image, but the latent space or the feature space is known to human. That's the main difference. In our latent space, essentially a feature space, these are the features understood by engineers. And we know in this process how it has it is converging. But in that process, it's a black box.
Okay.
I hope that makes sense. Thank you.
Any other questions?
Thank you for the great talk. I learned a lot from this presentation. So I have one question: that if we use this kind of process, do we need a lot of training data? And based on my understanding, it's quite expensive to get the training data in the material science. Can you give us some insight?
It's a very, very good question, and I also have an optimistic answer for that. With good news, no, you don't really need a lot of training data. So, say for without, yes and no. So without using descriptors, if you only use the standard generative AI, indeed you need a lot of training data. It's the same problem as you do the image processing, all these ChatGPT, Hunyuan, you name, Baidu. It's essentially driven by the data and computing power. You have to have the data. But once you introduce the knowledge, the existing knowledge, the descriptors, you don't. The data requirement then become the same as the traditional reconstruction method. You can start with one image often. Of course, you have more images, the result is better, but not so sensitive. So the data requirement using this method is exactly the same as traditional reconstruction method, no more, no less, but it gives the same quality of these, which require large amount of training data.
This probably assumes that all these descriptors are good enough to describe these materials.
Yeah.
Do you think this have very comprehensive coverage, or we might actually miss some important descriptors after many decades of research? And using the previous method, probably you are able to find some new features. These new features might be critical for the properties of those materials.
Yeah. Yes. It is a fair question, especially from the mathematics perspective. Because these are not rigorous maths. We know to capture fully the random field, the only way to do that is a joint property distribution. These descriptors, even use all of them, it wouldn't give you the comprehensive capture for sure. But for practical use, in the engineering field, you would have to trust the engineers are not all stupid. They have done their work, compared with experiments for so many times. So it's good enough, I'd say, in general. The descriptors are good enough, and they are more than sufficient, I'd say. Yes, in the literature, there are from 150 to 200 descriptors at that level. I don't have an accurate number in mind, but we are doing a piece of work with two of my PhD students at the moment to actually use our method to analyze all of them and condense them to a smaller subset. I can't tell right now because the work hasn't been completed, but I believe a much smaller subset would be sufficient in most cases.
Thank you very much for the information.
Okay, for the reason of time, we thank Professor Chenfeng Li for his great talk. Thanks for.
Thank you, everyone. Thank you.